Welcome to physics class. My name is Gias Uddin. My dear students, today we are going to discuss about another important article, numerical based on de Broglie hypothesis. Okay. So our first numerical problem is compute the wavelength of de Broglie wave associated with a proton with 5% of the velocity of light, and mass of proton is 1836 times of that of electron. Okay. So the given information of this question, solution, given velocity is 5% of light, 5% of speed of light. So we can write 5 by 100 into 3 into 10 to the power 8 meter per second. After solving this part, we can write 15 into 10 to the power 6 meter per second. So this is the speed of the particle. Okay. And mass of particle, this is 1836 times of mass of electron. So we can write 18 into 36 into 9.1 into 10 to the power minus 31 kg, because we know that mass of electron is 9.1 into 10 to the power minus 31 kg. So after calculating, we will get 1.67 into 10 to the power minus 27 kg. So this is the mass of the particle. And H is also Planck constant. H equals 6.62 into 10 to the power minus 34 joule second. And lambda equal what? Lambda equal what? We have need to find out lambda. So we know that by using de Broglie wave equation, lambda equal h by mb. Lambda equal h by mb. The value of h equals 6.62 into 10 to the power minus 34, and mass of particle equal 1.67 into 10 to the power minus 27, and velocity of the particle is equal to 15 into 10 to the power 6. After solving this part, we will get 2.64 into 10 to the power minus 14 meter. 10 to the power minus 14 meter. So this is our required wavelength associated with proton particle. Okay, for your better understanding, I am going to repeat it once again. Compute the statement of this numerical problem. Compute the wavelength of de Broglie wave associated with a proton particle with 5% of the velocity of the light, and mass of the proton is 1836 times that of electron. It means that, say, suppose this is a proton particle, and this proton particle, the speed of the proton particle B equal 5% of the 5% of c. It means that the speed of the light, and its mass equal 1836 into mass of electron, and mass of electron we know that 9.1 into 10 to the power minus 31 kg. So this is the rough concept of this numerical problem. So we can the information of the question, B equal 5% of light. It means that speed of the light, 5% of speed of light, 5% speed of light. Okay. So 5 into 5%, that means 5 by 100 into speed of light 3 into 10 to the power 8 meter per second. After solving this part, we will get 15 into 10 to the power 6 meter per second. M equal 1836 into mass of electron. Okay, mass of electron, that means 1836 times of the mass of electron. So 1836 into 9.1 into 10 to the minus 31 kg. After solving this part, we will get 1.67 into 10 to the minus 27 kg. And H equal Planck constant. This is equal to 6.62 into 10 to the minus 34 joule second. Lambda equal what? Okay. Now we know that by using de Broglie wave equation, lambda equal h by mb. When all the values substituted in this equation, then we will get 2.64 into 10 to the minus 14 meter. Okay, our next problem is the potential difference, the statement of this question. The potential difference applied between the anode and cathode. We know that what is anode and cathode. Anode and cathode, a CR tube is 100 volt. Assuming the velocity of the electron at the time emission to be equal to 0, find its de Broglie wavelength at the time of striking the anode. Okay, so the given information of this question, solution, given potential is 100 volt. Yes, potential is 100 volt. Accelerating potential or voltage is 100 volt. Okay, and electron Q equal charge of electron 1.6 into 10 to the minus 19 coulomb. and mass of electron 9.1 into 10 to the minus 31 kg, and Planck constant H equals 6.62 into 10 to the power minus 34 joule second. Okay, 34 joule second, 34 joule second. Okay, and we have to find its de Broglie wavelength. Yes, lambda equal what? Lambda equal what? So we know that by using de Broglie wave equation in terms of voltage, we know that lambda equal H by under root of 2m qb. The value of H equal 6.62 into 10 to the power minus 34, and 2 into the value of mass of electron 9.1 into 10 to the power minus 31 into 1.6 into charge on electron 10 to the minus 19, and accelerating potential difference 100 volt. After solving this part, you will get 1.22 into 10 to the power minus 10 meter, and this is equal to 1.22 angstrom, because we know that 1 angstrom equal 10 to the power minus 10 meter. So 1.22 into 10 to the minus 10 meter is equal to 1.22 angstrom. For your better understanding, I am going to repeat it. The potential difference applied between the anode and cathode, a shear tube, is 100 volt. Okay, assuming the velocity of a electron, particle is electron, this is clear that already. So the velocity of electron at the time emission to be equal to the 0, find its de Broglie wavelength at the time of the striking the anode. Okay, so the given information, potential, accelerating potential is 100 volt. Okay, electron, particle is electron, so the charge value of the electron particle is Q equal 1.6 into 10 to the minus 19 coulomb. Mass of electron is also 9.1 into 10 to the minus 31 kg. H is Planck constant, this is always constant. Okay, and lambda equal what? We know that by using de Broglie wave equation in terms of the voltage, so we can write lambda equal H by under root of 2 mqb. When all the values substituted in this equation, then we will get 1.22 into 10 to the minus 10 meter, and this is equal to 1.22 angstrom. Okay, our next problem is find the de Broglie wavelength of neutron particle at 127 degrees Celsius, given that Boltzmann constant K equal 1.38 into 10 to the power minus 23 joule per Kelvin. Also, Planck constant is equal to 6.625 into 10 to the minus 34 joule second, and mass of particle equal 1.666 into 10 to the minus 27 kg. Mass of particle, that means particle is Newton. Okay. So the given information of this question, we can write solution. Given Boltzmann constant K equal 1.38 into 10 to the power minus 23 joule per Kelvin. Planck constant is equal to 6.625 into 10 to the power minus 34 joule second. Okay, and mass of particle, that means M equal 1.66 into 10 to the power minus 27 kg. Okay, and lambda equal what? And temperature T equal 127 degrees Celsius. We know that degree Celsius is not SI unit of the temperature, so it should be converted in SI system. So we can write 127 degrees Celsius. This is 127 plus 273. This is equal to 300 Kelvin. Now we know that by using de Broglie, by using de Broglie wavelength in terms of temperature, lambda equal H by under root of 3 m k T. Okay, so lambda equal, the value of H equals 6.62 into 10 to the power minus 34. H equals 6.62 into 10 to the minus 34, and 3 into mass of particle equal 1.66 into 10 to the power 27 into K. Boltzmann constant is also 1.38 into 10 to the power minus 23 into temperature is also 300. After solving this part, we will get lambda equal 1.264 into 10 to the power minus 10 meter, and this is equal to 1.264 angstrom, because we know that 1 angstrom equal 10 to the minus 10 meter. So 1.264 into 10 to the minus 10 meter is equal 1.264 angstrom. For your better understanding, I am going to repeat it. Find the de Broglie wavelength of Newton at a 127 degrees Celsius, given that Boltzmann constant is this, K equal 1.38 into 10 to the minus 23 joule per Kelvin, Planck constant is this, and mass of particle is this. Okay. The given information of the question, K equal Boltzmann constant, this is K, and H is also Planck constant, M equal mass of the Newton particle, that means particle means Newton, here Newton. Okay. And T equal temperature 127 degrees Celsius, and this is not a SI unit of the temperature, so it should be converted in SI system. So 127 plus 273, this is equal to Kelvin. Okay, so 300 Kelvin. By using de Broglie de Broglie wave equation in terms of temperature, we can write lambda equal h by under root of 3 mkt. When all the values substituted in this equation, then you will write you will get 1.264 angstrom. Okay. Okay, our next problem is the statement of this problem. Compute the typical de Broglie wavelength of an electron in a metal at 27 degrees Celsius and compare it with the mean separation between two electrons in a metal is given to about 2 into 10 to the power minus 10 meter. Okay. So first of all, we are going to find out de Broglie wavelength. Okay. Solution. The given information of this question, particle is electron, this is clear that. So mass of electron equal 9.1 into 10 to the power minus 31 kg, and charge of electron equal 1.6 into 10 to the power minus 10 to the power minus 16 coulomb, and Planck constant 6.62 into 10 to the power minus 34 joule second. Okay, joule second. And temperature T equal 27 degrees Celsius, and this is equal to 27 plus 273. After solving this part, 300 Kelvin. Okay, and Boltzmann constant K equal 1.38 into 10 to the power minus 23 joule per Kelvin. So we know that by using de Broglie wave equation in terms of temperature, lambda equal h by under root of 3 mkt. Okay, the value of h equal 6.62 into 10 to the power minus 34, and 3 into the mass value of the electron 9.1 into 10 to the power minus 31, and K equal 1.38 into 10 to the power minus 23, and temperature is equal to 300. After solving this part, you will get the result is 0.62 into 10 to the power minus 8 meter. So this is our required wavelength of the electron. Now we are going to compare this value with separation between two electrons. Okay, separation between two electrons metal is given about 2 into 10 to the minus 10 meter. So separation between two electrons is also denoted by R naught. Okay, and R naught equal 2 into 10 to the power minus 10 meter. So we are going to compare between two value. Lambda divided by R naught equal the value of lambda equal that means wavelength 0.62 into 10 to the power minus 8 and divided by R naught 2 into 10 to the power minus 10. Okay, after solving this part we will get 31. So this is the comparison between wavelength and mean free distance, mean separation between two electrons. So this is always remember, this R naught is denoted by mean separation between two electrons, Okay, our last numerical problem is an enclosure filled with a helium is heated to 400 Kelvin. This is temperature 400 Kelvin. Okay, and a beam of helium atom emerges out of the enclosure. Calculate the de Broglie wavelength corresponding to the helium atom, and given mass of the helium atom is this. Okay, so the given information of this question we can write. Given mass of helium atom is 6.7 into 10 to the power minus 27 kg. Okay. As we know that generally mass of helium atom is is equal to 4 times mass of proton particle. Okay. So this is directly given. Mass of helium atom equals 6.7 into 10 to the minus 27 kg. Okay. And temperature is also T equal 400 Kelvin. 400 Kelvin. So Boltzmann constant K equal 1.38 into 10 to the power minus 23 joule per Kelvin, and H equal Planck constant 6.62 into 10 to the power minus 34 joule second, and lambda equal what? Okay. So we know that by using de Broglie wavelength in terms of temperature, lambda equal H by under root of 3m KT. 3m KT. Okay. So the value of H equal 6.62 into 10 to the power minus 34 under root of 3 into m. The value of m equals 6.7 into 10 to the minus 27. The value of K equal 1.38 into 10 to the power minus 23, and temperature, this is equal to temperature equal 400 Kelvin. 400 Kelvin. After solving this part, you will get 6.3 into 10 to the power minus 10 meter, and we know that 10 to the minus 10 meter is equal to 1 angstrom, so we can write 6.33 angstrom. So this is our required wavelength of helium atom. Okay. For your better understand, I am going to repeat it. The statement of this question: an enclosure filled with a helium atom is heated to 400 Kelvin. Okay. A beam of helium atom emerges out of the enclosure. Calculate the de Broglie wavelength corresponding to the atom, and mass of helium atom is 6.7 into 10 to the minus 27 kg. The given information of this question, mass is given already, mass is given. So mass of helium atom, mass equals 6.7 into 10 to the minus 27 kg. Temperature also given, T equal 400 Kelvin. And Boltzmann constant, this is also constant, so K equal 1.38 into 10 to the minus 23 joule per Kelvin. And this is Planck constant, H equal 6.62 into 10 to the minus 34 joule second. And we are going to find out lambda, that means wavelength of the helium particle. So we know that lambda equal by using a de Broglie wave equation in terms of temperature. So lambda equal H by under root of 3 mkt. When all the values substituted in this equation, then you will get 6.3 into 10 to the minus 10 meter, and this is equal to 6.3 angstrom, because we know that 10 to the minus 10 meter is equal to 1 angstrom. So we can write 6.3 angstrom. Okay. Thank you.